Welcome and thank you for joining this webinar from Orbit to Everywhere, Comprehensive Assessment of Modern Space Communication, prepared by Alpert Research Team. That rapid routing requirement leads directly to the need for a mesh in space.
This is perhaps the most significant technological leap in modern SATCOM, the implementation of high-speed intersatellite links, or ISLs. These advanced LEO systems use laser technology optical ISLs to create a dynamic mesh network right there in space. Laser communication offers several critical advantages. First, enormous throughput. We're talking 100 to 200 Gbps per link, which far exceeds RF limits. Second, extremely low interference because the laser beam is highly directional and very narrow. And third, latency. Light actually travels faster in the vacuum of space than it does in fiber optic cables on Earth. This reduces propagation delay significantly over long hauls of thousands of kilometers.
The strategic implication there is profound. By routing traffic satellite to satellite across oceans, they achieve a new level of resiliency and independence from the terrestrial network.
The space mesh bypasses reliance on vulnerable or geographically inconvenient ground gateways. It provides resilience, it improves security, and it allows the network to route data along the shortest possible path. This is often significantly faster than fiber across continents, offering what the Alpert Research Team highlights as a key competitive advantage in global data transport.
Let's delve into the brains of the satellite itself, the payload architecture. This choice really defines whether the satellite is just a passive mirror or an active, intelligent node in a network. We're talking about transparent versus regenerative payloads.
Right. The distinction is centered on where the data processing happens. The transparent payload, often called bent pipe, is the simpler heritage architecture. It receives the uplink signal, amplifies it, translates its frequency, and transmits it down. It's acting purely as a repeater in the sky. All the complex signal processing, error correction, routing, switching, that all happens on the ground.
Simple and reliable, but it means the satellite itself is relatively unintelligent.
Correct. The intelligence is centralized in the ground segment. Conversely, the regenerative payload, or onboard processing, OBP, is a fully active node. It receives the uplink signal, it demodulates it all the way down to baseband digital data, it decodes it, it performs routing and switching decisions based on the destination address, and then it re-encodes and remodulates it for the downlink. OBP is what enables the mesh architecture to decide where to send a data packet, which intersatellite link to use, or which spot beam to route it to. The satellite has to be able to read the digital header of that packet. This processing capacity is also a prerequisite for 3GPP Release 18 support for store and forward operation. That's where the satellite can temporarily hold data packets if the destination ground station or user terminal isn't immediately visible, and then it releases it once the path is clear.
And the ground segment is evolving just as fast, especially the user terminal, which is often the biggest cost for the customer.
We're seeing a huge shift from mechanical to electronic steering for antennas. The traditional parabolic reflector, the dish, is high gain and simple, but it's heavy, bulky, and needs motors to point it.
Fine for a fixed location, useless if you're moving.
Exactly. The revolution is the phased array antenna, or ESA, electronically steered antenna.
The flat panels.
Right. These flat panels use software to control thousands of tiny elements that steer the beam electronically instantly with no moving parts.
And for LEO, that's not just a nice to have, it's mandatory.
It's absolutely mandatory. You have to track satellites moving at thousands of kilometers per hour across the sky. ESAs are the essential enabler for SECOM on the move on planes, trains, and ships.
Let's look at the core subsystems that keep these things running.
The bus subsystems are just feats of engineering. You obviously need power generation, which is solar arrays, and storage, which is batteries.
You need to stay pointed in the right direction.
That's the attitude and orbit control system. You have reaction wheels and gyroscopes to maintain orientation, and modern LEO sats use highly efficient ion thrusters for station keeping and making those little orbital adjustments.
And space is a place of extreme temperatures.
Extreme. So thermal control is critical. You have radiators, heaters, insulation. You have to manage swings from over 120 degrees Celsius in the sun down to minus 150 in shadow.
And the brain of the operation.
The command and data handling, or CNDH, subsystem. That's the onboard computer that runs everything, receives commands, and sends back telemetry on the satellite's health.
Moving to the operation side, how do operators maximize the capacity of a satellite's limited spectrum? This must require a lot of sophistication in antenna design and network management.
It starts with the antenna design, multi-beam antennas and spot beams. Instead of a single wide beam covering an entire continent, Modern high-throughput satellites generate many narrow, high-power spot beams. This allows for extensive spatial frequency reuse.
Meaning the system can use the exact same Ka-band frequency in two geographically separated spot beams simultaneously without them interfering with each other.
And this spatial reuse vastly multiplies the overall spectral efficiency. Dynamic beamforming allows the operator to shape and steer the beams, directing maximum power and capacity to areas where demand is highest. Consider a sophisticated system. This system performs a comprehensive network-wide link budget analysis. This near real-time assessment allows the network to dynamically switch the carrier type, moving traffic away from a static time division multiple access, or TDMA, to a more flexible burst mode, wave switch, or single channel per carrier operation. It's optimizing modulation and coding for the instantaneous link condition. This dynamic approach ensures maximum bandwidth use and has been shown to achieve throughput gains of up to 15% compared to using static, pre-allocated methods.
Finally, let's talk about the big operational reality of LEO, orbital safe, collision avoidance. When you put thousands of things up there, the risk of a Kessler syndrome cascade is real.
It's a daunting mathematical problem. When two objects get close, a conjunction event, you have to calculate the probability of collision, or POC.
Which is not simple.
No, it's a complex calculation that requires constant, precise monitoring of every object.
And if the risk is too high, you have to move.
You perform a collision avoidance maneuver. This is typically a bi-impulsive maneuver to separate thruster burns to change your trajectory.
And the timing on that is critical for fuel, right?
The FCC now requires new LEO satellites to be able to actively maneuver and, crucially, to deorbit within 5 years of their mission ending.
Down from 25 years.
A huge change. It's a massive improvement for orbital hygiene and long-term sustainability.
The transformation is just undeniable.
It really is. And what's so fascinating is just how quickly all these pieces have come together to take satellite from being this niche, high-latency tool into a core, competitive part of the global wireless backbone. This overview from the Alpert Research Team should really give you that full integrated picture.
Modern satellite communication has evolved from a specialized broadcast tool into a core pillar of global connectivity, enabling broadband, IoT navigation, and resilient communication infrastructures. With the rise of LEO constellations, AI-optimized networks, and 3GPP standardized NTN systems, satellite communications are poised to serve billions of users and devices worldwide. This Alpert Research Team overview delivers an integrated view of the technologies, architecture, applications, challenges, and opportunities shaping the next decade of satellite-enabled connectivity. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.